Hey guys, what's going on? So today we're going to be talking about conformal Riemann curvature. This is the next step into understanding the Weil tensor. This is forewarning. This is going to be a very math-heavy video, and so if you want to skip this video and wait till the video on the Weil tensor comes out, then you feel free to do that. Here again, we're just going over a lot of really heavy math before we get into future fun stuff. Okay, so with that being said, make sure to hit that like and subscribe button. Make sure to go on to my Patreon page or become a member here. And without further ado, let's get right into the topic. So we are calculating the connection coefficients first under conformal transformations. Okay, so there's going to be a little bit of notation here. The notation is that wherever we see a line above our elements, that's the line indicates the conformal transformed, or the conformally transformed object. So what we established before is understanding how we got conformally transformed connection coefficients. Okay, and this was the formula for that. So what we're going to do now is we're going to replace these guys all with the formula for our conformally transformed metrics. And what we get is all of these guys right here. Okay, so everything here is conformally transformed. Okay, and our derivatives come from the 2 times this here because, again, we sort of talked about this in an earlier video, but whenever we have this derivative here, we're taking, we need to take we're taking the derivative of this squared, right? So this 2 is from the exponents in this function, okay? This conformal transformation function. In short, this is just the dropping the exponential. This is standard calculus sort of stuff. Okay, and then we get to this point where we can collect all colored terms. Okay, this is what I'm doing, collecting all colored terms, and then and of course this should be blue also, but. So now we have this here, and we can see that this here is just our connection coefficient. So the conformally transformed connection is equal to the non-conformally transformed connection plus all of this here. Okay? And what I'm going to try to do throughout this video is color code a bunch of stuff so that things are easier to understand and follow. Okay. Excuse me. So we now calculate the Riemann curvature under a conformal transformation. So the Riemann curvature, the conformally transformed Riemann curvature is this guy, and everything is conformally transformed. Okay. So we're going to take this guy here, and we're going to rename indices. We're going to shuffle things around to get these terms, and then we'll get these terms as well, and everything is going to come together quite nicely in the end. Okay? So, let's begin. Let's start off by calculating these 2 guys and taking their difference. And then we'll put a pin in that. We'll calculate these guys, and we'll put everything together. So, this is going to be, we're taking these definitions, right? So this is this definition and this definition. We're going to subtract the 2, okay? And when we do that, we can see that these terms are going to cancel, okay? And so we get this term minus this term, which is on this side of the equation, equals all of this garbage in here, right? So this is pretty long and disgusting, but we're going to put a pin in this now, and we're going to come back to it because we're going to see things canceling out. So Now we calculate the third term in the Riemann curvature tensor. So that's this term right here, all right, which is right here. And so this is really, we're really just multiplying definitions of the connection coefficients. Okay. Okay. So I color coded everything to follow, so we can follow things through and go relatively quickly through all of this. So the first term is this times this. Okay, and then we have this term which is here, this term which is here, and this term which is here. Okay, and we're factoring out this this term here. Okay, and then the other three terms here, but then we need to multiply this with this guy, this with this guy, and that's what we're doing here. So the yellow terms multiply, sort of foiled out with all of these, and then the green terms foiled out with all of them, and then the blue terms foiled out with them as well. And we can see that we get, so this term here times this is right here, this term here times this is right here, and this term times this is right here. So everything is foiled out. You can pause the video at points if you want to. We can see here that this term is equal to this right here. This is this here, so I'm just rewriting things, and we can rewrite this in terms of the Kronecker delta. Okay, and then the Kronecker delta is going to drive some indices to be different names, right? So lambda is going to be sigma, and so we get this term right here equaling this. Why is that important? Well, that's important because we'll be able to reduce a few things now. So everything is the same here. Okay, the only difference now is that we have this term. All right. Okay, so thankfully I color coded all of this because it would have taken me forever to sort of get my bearings on trying to explain this. So this is true. I think color coding this was probably a really good idea. It took me a while to do this, but I wanted to be detailed and as succinct as I possibly could. So now we have, okay, so we have this, which is all of this in here, okay? And you can follow all the color coding, okay? You follow all the color coding to make sense of all of this in here, okay? And then when we rename indices, right? So we have kappa mu nu, kappa sigma mu, right? So we come back up here, kappa sigma mu. This is just this other term, right? So we put a pin in this guy, all right? And now we've calculated these two guys. Now it's time to subtract these two terms, because again, we're doing that right here. We're subtracting them. So we're taking the difference of these two guys, and then we take the difference of these two guys, and then we add them up. All right. So let's go ahead and do that. So we have this term and this term. We're going to subtract the two. So this minus this. All right, and when we do that, we have all of this, right? All this garbage minus all this garbage. Garbage minus garbage is equal to this garbage right here. So a lot of things are going to cancel out. So let's see. So these two guys will this guy here will cancel out with this guy with this guy, and this guy with this guy. All right, so we get this term minus this term is all of this. Putting everything together now, the conformally transformed Riemann tensor is this guy. It's going to be, again, the difference between these two plus the difference between these two. And so we have the difference between these two, and the difference between these two is all of this in here. Okay. Okay, so this is, okay, so I'm not gonna, so what you can do is, you could pause the video here, but essentially what I'm doing is, I'm subtracting, I'm taking all of this, right, so these two terms are these two first terms right here, okay, and then you can see all of these where we have the inverse of the transformation, and they're all right here. Inverse transformation. So all of these guys, okay, that's all of these guys up in here. And then we have the difference between these two terms, which is right here. These are the unconformally transformed ones, which is what we're seeing right here. And then all the other terms are right in here. All right, so that's a lot. It's a lot. We're still not done. I'm gonna keep on color coding here so that we can follow things through. But eventually we're gonna get to a point where things actually collapse down pretty nicely. So here, so we have this here and this here is the original Riemann tensor. So that's the original Riemann tensor. This is the conformally transformed Riemann tensor. And then we have a lot of terms in here that we can actually see. So I'm going to highlight in blue, yellow, and green. All right, and then all this stuff in here we'll deal with later. For the blue highlighted equations, we have these two terms, which is right here, and this right here, which is right here. And we can see that, again, I'm highlighting this term here and this term here. We're actually just factoring things out, right? So here's our inverse metric, here's that inverse metric. And then we have the d sigma, so that's the d sigma. So these guys with this guy, we're bunching together, and then we're seeing that this guy, we're bunching together with this guy right here, and we get this, okay? So, okay, that's all fine and good, because these are just definitions of derivatives, right? So this times this guy here, let's see, and then we have all of this here. Here's that inverse, and here's sigma mu, or omega mu, okay? Okay, so, and the reason we go from here to here, or from this step to this step, is because we can see that we have, again, this is a definition of a derivative. All right, so we're bunching in this into here. Okay. This is sort of the covariant. This is a definition of a covariant derivative. So we're just this. So one way of thinking about this is where you can actually go from this point to this here. Okay, this is again, that's just the definition of a derivative, and we're doing. And then for these terms here, these are the orange terms up here. We have something similar going on where we have the inverse metric and the, so here's our green term. And then our, this term here is right here, okay? So let's take a look at this term. So all of this here, and what we're doing is we're factoring out. You could sort of see how this works just by pausing the video, but we're factoring out this inverse right here, which is right here, and then we are taking this term right here and we're subtracting it with this term right here. And again, I don't want to belabor the point here. There might be points in this video that might behoove you in pausing the video just to absorb as much as you can here. Here, these terms we're adding 0. And then we can get, so once we get this here, we can understand how we got this, and then we see that we can bunch things together as well. So we're bunching these guys, and then we're subtracting, so this term here is right here, and then we have this term here is right here, and then this term here is right here, and then this we can see is, or we have definitions of covariant derivatives of metrics, right? Whenever we sort of went over this in our tensor calculus class, but this is the definition of the derivative of a covariant, of a completely covariant 0-2 form, okay? And we have, not form, right, a completely covariant 0-2 tensor. And then we get this, and this here is 0. And so we get this right here. Okay. So we saw some things went to 0. So these orange parts went to 0. Let's take a look at the green. For the green highlighted equations, we have this right here. Again, we can follow, you can pause the video if you want. You can, we have this term here, and then, again, you could sort of see how this works. We have this term plus this term here, because a minus times the minus gives us the positive sign, and then we get all of this as well. Okay, and so now, right, so again, this negative sign is right here, and then we have this term right here. Okay, and so now we can get from here to here, okay, and we can see in order to do that we have, so this term here, and we're defining covariant derivatives again, so the derivative of this guy here is right, we have this term and g mu nu, or g mu sigma, right? So g mu sigma, and let's see here, right, so this term is for this one then, and then this term is for this one, and then we can see the derivatives take place here, right? So this here, this comma mu or nu is this guy right here, and then this comma sigma is this guy right here. Okay, we're getting there. And then we have, so this reduces down to this. Okay, we're just taking the metrics out. The conformally transformed Riemann tensor in terms of covariant derivatives is therefore all of this. Okay, so we're putting everything together, right? So we're putting this together along with the other ones, the other things that we found out, okay? And then also, really quick, we have this term here that we never dealt with. So that is this term down here. Okay, so we're color coding again. And to color code, we have green, right, yellow, red, brown, and you can, so I'll kind of maybe speed this up a little bit. You can pause the video if you want to really absorb things, but we're going to get from here to here relatively quickly, and then I've underlined the terms that are that we can follow then. So this red underlined term is going to be associated with this term here, and then this brown underlined is this one, and then green and purple underlined are here these guys, okay? And then now I'm color coding. Okay, so I color code these guys as well. So these guys, these colors here, and the yellow and green are also color coded in our indices. So we've gotten to a point now where we can say the Riemann curvature tensor, or the conformally transformed Riemann curvature tensor, is the Riemann curvature tensor plus what looks to be 4 copies, or 2 copies, or 4 copies of some tensors that might be interesting to us. And those, we're going to define those new tensors now as these B tensors, right? So B tensors in the first 2 cases are being contracted, or not fully contracted, but they're being multiplied by the metric. That's these 2 guys, and then here they're being multiplied by the Kronecker delta times the metric, right? So that's these 2 guys right here. All right, and then tau and sigma is how we're gonna label these guys. So tau and sigma right here. Okay. And so this is our newly defined Riemann curvature tensor in terms of these B tensors. These B tensors, okay, so I'm defining what they look like right here. And we can see that this guy here, I'm just copying it right here, this is equal to this here, so taking this equation, or taking this identity, we then multiply this by this metric to get this right here, okay? And we can add terms to each other here to get this 2, right? So this is going to add with this guy here, because we have these inverse metric times inverse metric, so that's to the -2. That's where we're getting this -2 here. And then we have this term here, which is right here. All right. Okay, so we have this here. We can lower the indices of this tensor. So when we lower the indices, we're just multiplying by the metric. And that's what we're doing up here, right? And so when we do that, we multiply by the metric. When we multiply by the metric, we get this, and then we get this guy right here. All right, we're almost there. So we have these new metrics, or these new tensors, right? This B kappa lambda tensor, which looks like this. And this, we could see here that we have an inverse of the conformal transformation, a -2 inverse of the conformal transformation, and then we have this term right here as well. Okay, so let's keep on going. And what we've essentially found, right, well, these guys are going to play a role. These guys play a role in understanding how the Riemann curvature tensor is defined. So this is the definition of that tensor, and we've reduced these guys to look something like this. Okay. We can also calculate the trace of the tensor. So to do that, we're just identifying all of the we're taking this guy here, or we're taking this guy here. We're identifying all the lambdas with kappas. Okay. We get this right here, and then to get from here to here, we can swap k for mu because they are dummy indices. And then we get this here, okay, and then we get this right here. So this is where we're starting. The m here is the so let's just break this apart here. The m is the dimensionality of the manifold, right? So kappa times kappa, that's just a trace of kappa, so that's the dimensionality of the manifold, right? So that's m, okay? That's where the m comes from. So we get all the way down to here, okay? And so in summary, we have our conformally transformed Riemann curvature tensor. The conformally transformed Riemann curvature tensor has these B tensors in them. So these B tensors are really what's driving the conformal transformation. Okay? So maybe we should make a note of that because that's important to know. So these things drive So these beta terms drive the conformal transformations. And then from the beta, then we can define the B terms, and then we can define the trace of the B terms also. And the trace of the B terms contains the dimensionality of the manifold. So the trace contains the dimension. So their trace contains dimension. So you can imagine, well, if we're in space-time, what this actually reduces down a bit more, because in space-time our dimensionality is 4. So 4 minus 4 is just 0. So all of this is going to go to 0. And so we just get this right here. But if our dimensionality is bigger than 4, then we get we have this additional term, the square inverse of this conformal transformation begins to take hold. If our dimensionality is less than 4, again, this also takes hold, but in a negative way. Okay? So 4 is there's a sweet spot here. The sweet spot is a dimensionality of 4 really reduces this beta, or this B tensor, or its trace, to this. Okay? And so we're pushing on 30 minutes here. So I'm going to stop. And in the next video, we're going to take all these tensors and understand them within the context of the Weyl tensor. The Weyl tensor is something that you typically hear about more in more advanced GR courses. With that being said, we're going to go through it in great detail. And if you like this kind of content, make sure to hit the like and subscribe button. Make sure to go into my Patreon page if you want to support the channel or become a member. And with that being said, I'll see you guys in the next one.